Okay, let's continue talking about infinite sequences. This is probably the most useful property we've talked about. If you think of a sequence, the terms of a sequence, as being the specific points on the graph of a function at the integer values 1, 2, 3, and so on, these points here, then if the entire function is getting close to a limit L, then so would the specific points, which are the terms of the sequence, you see. And also the limit laws from your Math 151, especially section 2.3, all those limit laws would apply then. So if you had a sequence like this, whose general term is given by the square root of inverse tangent of n, we could think of this as a sequence starting with 1, 2, 3, and so on. We do have a property that says as long as this is a positive number, you can take the limit inside the square root, like this. And we saw before the graph of the inverse tangent of x is getting close to pi over 2. So the integer values of x are also getting close to pi over 2 as n gets large. So inside the square root you get pi over 2, so the answer would be the square root of pi over 2. Speaking of limit laws, remember this good old squeeze theorem? The squeeze theorem applies for limits as well. If you have the nth term of a sequence being between two other nth terms of sequences, and if as the n goes to infinity, if this term is getting close to L and this term is getting close to L, since this is in between them, it has to get close to L also. So that can be helpful when you want to compute certain limits. For this one, you may kind of figure it out. It looks like it's 0 because the bottom is getting close to infinity and the top is somewhere between 0 and 1. But to show it clearly, the squeeze theorem is helpful. Notice that since we have sine squared, the sine squared of n is always between 0 and 1, right? Okay. So when you divide everything by 2 to the n, you see that sine squared of n over 2 to the n is always between 0 and 1 over 2 to the n. If you look at the graph of 1 over 2 to the x, you can see that the entire graph is getting close to 0. So this limit of 1 over 2 to the n also gets close to 0. So since the left side gets close to 0 and the right side gets close to 0, the thing in the middle must get close to 0 also by the squeeze theorem. Pretty nice, huh? Here's another property that's kind of nice for computing limits of sequences. If the absolute value of the nth term is getting close to 0, then doesn't the nth term have to get close to 0? That should be obvious too. Anyway, so that can be nice when you have something like this. Notice this is not a positive term sequence. Cosine of n, it gives you kind of a random point on the cosine function, enters your values of x. So some of these are negative, some of them are positive. So this oscillates between positive and negative numbers. It might be helpful to first take the absolute value of a sub n, and then what you know, if you have the absolute value of cosine of n, isn't that always less than or equal to 1? Got it? This numerator is always between 0 and 1. Therefore, this is true. The absolute value of this is always greater than 0. But it's always going to be less than or equal to 1 over n plus 1 because the numerator can never be bigger than 1, right? So we're going to take the absolute value and now we're going to apply this squeeze theorem again. The limit of the left side is 0, obviously. Limit of the right side is 0. You can apply your limits from Math 151 for that. That's obvious. So by the squeeze theorem, the limit as n goes to infinity of the absolute value of cosine over n plus 1 is 0. And then by that theorem we just said, if the absolute value of the nth term is getting close to 0, the nth term is getting close to 0 as well. Let's look at a few more sequences here. This one. If this is the nth term of the sequence, the question is, what is the limit as n goes to infinity? Well, the limit as n goes to infinity of a sub n, you might recognize this limit, by the way. But it has the form, the base is getting close to 1 and the exponent is getting close to infinity. 1 to the infinity is actually an indeterminate form. So you remember how to handle that? The way you handle that in 151, we took the limit of both sides first. Well, let's first call this a sub n y, and then take the limit of both sides. You get this. You can bring the exponent down. Now, when you take the limit of ln of y first, we're going to take the limit as n goes to infinity of ln of y, find out what that limit is, and then the limit of y, which is a sub n, is going to be e to whatever this limit is. You got it? We're going to compute the limit of this expression, and whatever, if this expression were, say, 2, the limit, then if ln of y is getting close to 2, y would be getting close to e to the 2. You see? Anyway, that's how it works. So okay, so let's do that. What form does this have now? When you have the ln of y, it looks like it's going to be infinity times 0. Infinity times 0 is also, this has a form infinity times 0. This is an indeterminate form, but remember what you do there? You algebraically, you play around with it. See this n, you put 1 over n on the denominator. And then now it has the form 0 over 0. You can apply L'Hopital's rule to this. When you take the derivative of the top, let me see this here. Here we go. When you take the derivative of the top, you get 1 over 1 plus 1 over n times the derivative of what's inside. The derivative of what's inside is just negative 1 over n squared. The derivative of the bottom is negative 1 over n squared. But look, the negative 1 over n squareds cancel. So the limit as n goes to infinity of 1 over 1 plus 1 over n. I think that's pretty easy to see. It's 1. So we've shown that the natural log of a sub n is getting close to 1. So, or the natural log of y equals 1, so the limit as n goes to infinity of y, which is the limit as n goes to infinity of a sub n, is e to the 1, or e. And perhaps now you recognize this. This is a definition of e. 1 plus 1 over x to the x, the limit as x goes to infinity. This is one of the ways we defined e. Alright, let's do a couple more. Some of these are kind of sneaky. This is kind of sneaky. This one isn't obvious at all, I don't think. The limit as n goes to infinity of a sub n, n factorial over n to the n. They're clearly both getting large. So if you write out what a sub n is, isn't it the factorial of n? So it would be 1 times 2 times 3 all the way up to n. And the bottom is just a bunch of n's, n factors of m. However, if you group it just right, pull off the first factor, 1 over n, and pull that away, and look at everything else. Every one of these you have a 2 over an n, a 3 over an n, and so on. This expression here is less than 1. Do you see why? This thing in parentheses is less than 1? It's because the numerator is smaller than the denominator. So as long as n is greater than 2, what we've shown is that a sub n is going to be less than 1 over n, because this factor here is less than 1. You see where we're going now? So a sub n, this expression here is between 0 and 1 over n for n greater than 2. So let's apply the squeeze theorem yet one more time. This limit is 0, obviously. This limit is 0. So therefore, by the squeeze theorem, the limit of as n goes to infinity of a sub n is also 0. Pretty nice, huh? I knew you'd like that one. Okay, suppose we have the sequence a sub n equals 1 to the n, and we want to know whether the sequence converges or not. If you look at the graph of y equals 1 to the x, that's a horizontal line, right? So from the graph of y equals 1 to the x, you can conclude the limit as n goes to infinity of a sub n is 1. The sequence converges to 1. Okay, how about the sequence whose nth term is a sub n equals 2/3 to the n? Again, you can look at the function y equals 2/3 to the x. This is an exponential function whose base is less than 1, so it's decreasing. It has a horizontal asymptote at 0, right? So from the graph of y equals 2/3 to the x, you can conclude limit as n goes to infinity of a sub n is 0. The sequence converges to 0. How about this one? Looking at the sequence whose nth term is negative 1 to the n. If you just write the first couple of terms of the sequence out, you see that it oscillates. The a sub n's aren't getting close to any one thing. So since a sub n oscillates, the limit as n goes to infinity of a sub n does not exist. So we would say the sequence diverges. Okay. This one, again, we can go back to the graph of exponential function. In this case, 3/2 to the x. This is an increasing exponential function since the base is bigger than 1. So the limit as a sub n goes to infinity is the same as the limit as x goes to n. And in other words, since the graph is going to infinity, the a sub n's are points on the graph, so they're also going to infinity. In this case, we'd say the sequence diverges. So this is a very important theorem we're going to use next section when we talk about infinite series. But when you have a sequence and of this form, a number to the nth power, as long as r is between -1 and 1, it converges. If r equals -1, it diverges. We just showed that. And if r equals 1, it converges to 1. So if r is any other value besides between -1 and 1, it diverges. Now, in fact, if r is between -1 and 1, but not equal to 1, it converges to 0. And if r equals 1, it converges to 1. So this is a nice little theorem to use because sequences of this type come up quite a bit. All right, let's do one more. All right, so let's look at this one. This is a sequence written like this. You could play around with a little bit. If you look at a sub n, couldn't you pull off a 2 to the 2 from here? So 2 to the n plus 2 is 2 to the 2 times 2 to the n. So what you could do is this is 4 times 2 to the n over 3 to the n, which can be written like this. Now it'd be easier to see what the limit is as n goes to infinity. Limit as n goes to infinity of a sub n is this, and the 4 factors out. And since r is between -1 and 1, this r 2/3 to the n goes to 0. So we'd say the limit as a sub n equals 0. So the sequence converges to 0. All right, we'll see you next time. Bye-bye.